India, the project in Dubna, so and other talks, very interesting ones. And I guess the discussion session will be very interesting. So looking forward to that. And then, without further ado, I give a word to Professor Kirill Bugayev, who will be a chairperson and also a discussion leader of this very important session. So please, Kirill.
Thank you, Roman, for introducing me. So let's start our session. I welcome, there are 31 participants. I welcome everyone. And so Professor Luo, please, it's your turn. You have 28 minutes approximately, and please reserve a couple of minutes for the discussion or for short questions, okay?
Okay.
Thank you.
Yeah, okay. Sorry, Xiaofeng, we can see only black screen. Can you stop sharing and then start it again, probably? Just some kind of glitch, I'm not sure.
Okay. Can you see my screen?
Yes, now it's perfect. Yeah, thanks.
Oh, okay. So good morning, everyone. I'm Xiaofeng Luo from Central China Normal University. I would like to discuss with you about status and progress on the search for the QCD critical point in heavy calculations at RHIC. So you know that actually in our middle school science class, we know that the water has three states: ice and liquid water and a gas. So actually we know that the matters will go in phase transition by varying the external condition. For example, the pressure and the temperature. The right-hand side show you the phase diagram of the water. You can see that how they change their phase with different conditions. Because this water phase transition is dominated by electromagnetic effect, so that we see those phase transition happens around 100 degrees. We have also the first order phase transition, land, and also the critical point. And at critical point, we know that the correlation length will diverge, and also the divergence of the thermodynamic quantities, such as the specific heat. Actually, the phase transition is happening because of the competition between the thermal motion and the interactions. So if you don't have interaction, basically you will not have phase transition, or if you only have this, for example, the free gas. So actually, the phase transition is competition between them. For example, the van der Waals interaction that we know very much, that it has both the attractive interaction and also repulsive interaction due to the size of the molecules. And please go to the slide 3. That actually, so the water have phase transition around 100 degrees. Then if we heat the matter to 1 trillion degrees, then what will happen? Actually, at such high temperatures, the form of the matters basically is made of the free quarks and gluons. And this will form a new form of the matter called the quark-gluon plasma, which exists at the early universe after the Big Bang. And experimentally, we can actually collide in two nuclei to create such extreme conditions. This allowing us to study the properties and the phase transition of this QCD, hot QCD matters in the controlled conditions. So this is actually a conjectured QCD phase diagram. You know that the y-axis is temperature, the x-axis is baryon chemical potential. Actually, we know not too much about the QCD phase diagram, except at a 0 baryon chemical potential from hadron resonance gas to quark-gluon plasma is a smooth crossover that we know from the lattice QCD calculation. And the transition temperature is around 160 MeV. And at a high baryon density region, that by many effective model calculation, it is suggested that it's of the first order phase transition between these two phases. Then if those are both true, at the small mu b is the smooth crossover, and at high mu b is a first order phase transition, then we know that there must be a QCD critical point as the endpoint of the first order phase boundary, which is called the QCD critical point. So a key question is that whether there is a QCD critical point at a finite baryon density region, and also whether we can map out the first order phase transition boundaries experimentally. And if we confirm those structure in QCD phase diagram, actually it will greatly enhance our understanding of the universe evolution and also the structure of the visible matter. And you can see at this QCD phase diagram at high temperature region, it is related to the our universe evolution, and also at a high baryon density is related to the dense object in astrophysics, which is happens in our nowadays. So understanding the phase structure at high baryon density region is extremely important to understand and also connect it the early universe and the universe nowadays. Actually, that from the theoretic side, there are a lot of prediction about the location of the QCD critical point in the phase diagram. Here, I just show you a compilation from some result from lattice QCD and the Dyson swing equation, also functional normalization group theory, and also as some effective model calculations. You can see that the result from those computations spread a wide region in the QCD phase diagram. So that means we still have large uncertainty for the theoretical estimation of the critical point location. Experimentally, actually a lot of efforts have been made to trying to explore the QCD phase structure at high baryon density region, and also search for the possible QCD critical point. And currently, the ongoing experiment, for example, the RHIC-STAR beam scan program is ongoing. Its first phase beam scan has been complete in 2017, and currently the second phase beam scan is ongoing. And also two lower energy experiments are under construction: the MPD experiment at the NICA, and also the CBM experiment at the BES-I fair. The NICA is a collider experiment, and also the CBM experiment is a fixed target experiment. And also there is an experiment called SPS, which is a fixed target experiment in CERN, and this is its energy range. So you can see that actually in the coming future, exploring the QCD phase structure at high baryon density is a very hot topic in near future. And the relativistic heavy collider that I'm working on, that is in Brookhaven National Lab at the US, and the STAR experiment is located at the 6 o'clock is at the RHIC-STAR. And actually, it's the RHIC accelerator energy it can vary from 200 GeV down to 5 GeV per nucleon pairs. And it's also the highest energy polarized proton collider. Its top energy is the center of mass energy is 500 GeV. And this is our star detector system that you can see that there's in the center of the star detector system is a time projection chamber, which can be used to do tracking and also particle identification with this energy loss. And in the barrel position, there's a so-called the time of flight detectors, which can be identified the particle with high momentum. So that means it can extend the PID capabilities up to higher momentum regions. And it has large uniform acceptance of the middle rapidities with 2 pi azimuthal, and the eta range is ±1. So, and also it will provide you excellent particle identification. And this is a data set that has been collected since 2010 till 2017, which is the first phase of the RHIC beam scan. We have collected energy from 200 GeV down to 7.7 GeV with those data energy point, and also the corresponding number of events. From this energy, actually, with some formulas, the parametrized formulas, we can obtain the so-called the chemical phase mu B and the temperature. And we can see that by tuning the colliding energy, we can access a border region of the QCD phase diagrams. For example, its mu B is around can be varied from 25 MeV to 420 MeV. That is wide regions. And we have a advantage of this collider experiment that because for different energy and also different particle species, our acceptance is rather uniform at middle rapidities. That will minimize our seismatics when you're doing the beam scan to search for the QCD create point. So you can this plot just show you how the chemical phase out is close to QCD phase boundary. You can see the left plot show you this the green band is QCD phase boundaries that from the lattice calculations, and also the data point from the RHIC beam scan. The yellow band is from some fit to the chemical phase point of the data. It's some parametrization formulas that you can see that actually the chemical phase obtained from the experimental heavy calculations are very close to the result of the QCD phase boundary from the lattice. This is very important because we are trying to see, search the signal of the phase transition. So it's very important that our chemical decoupled temperature of the system is very close to the QCD phase boundary. And the right plot shows you this very famous K-pi ratio as a function of the collation energies. And you can see this famous non-monotonic energy dependence of this K plus over pi plus ratio as a function of collation energy with a peak around 8 GeV. And the green band actually is from the thermal result, thermal model result. You can see that those data points can be well described by thermal model calculation. And also based on from the thermal model that below 8 GeV, there's a baronic dominant, and above 8 GeV actually is meson dominant systems. So we can define high baryon density regions between 2 to 8 GeV. And in order to search for the QCD create point, we need to very sensitive to observables. For example, experimentally, we now we're using the so-called the higher moments of the conserved charge distribution and also the light nuclear productions to search for the QCD create point. Due to that, we will met the large density fluctuation and also baryon clustering in the vicinity of the QCD create point and the first order phase transition. So the experimental signature of the create point will be that the non-monotonic variation of those colliding energies for those experimental observables. The first sensitive observable I want to discuss with you is so-called the light nuclear production. The light nuclei production actually from the theoretical model prediction that due to this very large density fluctuation and baryon clustering in the vicinity of the critical point, and also based on the coalescence model, is the yield of this light nuclei will be affected by this so-called the nucleon density fluctuations. You can see the term here. Then if you can see some coefficients in the front that in order to be compared to experimental measurement that which is easily measured, we need to construct the yield ratios between different particles. For example, the triton times neutron yield divided by neutron yield square. By constructing this yield ratio, you can see that it's sensitive to the neutron density fluctuations. Experimentally, we can measure the left side, whether it is then to see whether this observable has a non-atomic energy dependence. The light nuclei production actually is has been studied a long time ago in heavy ion collisions. And in traditional nuclear energy, we know that those light nuclei actually with very small, a few MeV bonding energies. And also, we know that in heavy ion collision environment, it is with very high temperatures, with 100 MeV. So one natural question is why we can still observe light nuclei production in such hot environment in heavy ion collisions, and it can also be well described by the thermal model predictions. You can see, so that's actually need to be understood. It's also connected to the production mechanism, whether it's a coalescence or microscopic interaction, and also thermal production of those light nuclei in heavy ion collisions. And this is also important to search for the phase transition signal with this light nuclei before we can understand the light nuclei production mechanism. So experimentally, we have actually measured those production of the deuteron and triton in the RHIC beam scan. And you can see that we can identify those light nuclei with time projection chamber and also the time of flight. And we can extract those deuteron and the triton signal and you can see the background is small, and we can extract those light nuclei production. But we still need to do many corrections before we obtain the environmental spectrals. And this slide just shows you this result of the deuteron and the triton production from the first phase of the beam scan at RHIC from 7.7 GeV to 200 GeV. The left side is the deuteron, the right side is the triton productions. You can see for different collision centralities. By integral those spectral, we can obtain the DNDY at middle rapidities. And by obtaining the DNDY of those light nuclei, the deuteron, triton, then we can obtain the so-called particle ratio between the deuteron over proton and the triton over proton, and as a function of the collision energy for most central collisions. You can see that both deuteron over proton and the triton over proton show a decreasing trend as when we increase the energies. And also the deuteron over proton can be described by the thermal model results, thermal model calculations. However, from the triton side, you can see that our triton result at RHIC energy and below deviate from the thermal model prediction. But from Alice result at the 2.76 TeV result, it follows thermal model prediction. So this is still a puzzle why the triton result at RHIC energy and below deviate from the thermal model prediction. And then we plot this light nuclei yield ratio triton times proton over deuteron square, and as a function of the collation energy for 0 to 10 centrality, which is central collations. You can see that we see a clearly non-monotonic energy dependence behavior with a peak structure around between 20 to 30 GeV. And at a low energy, which below 20 GeV, our results are consistent with the result from the NA49. We also have done transport model studies. We can see that our transport model calculations basically show flat energy dependence, and which cannot describe the experimental data. But I will in the transport model calculation, they don't have any phase translation physics in those transport model. So now the second sensitive observable that we use to search for the QCD point is the so-called the higher moments of conserved quantities. From theoretical prediction that the higher order fluctuations have a higher sensitivity to the correlation length of the systems. And also, if we take the cumulant ratios, the ratio of those cumulants, then we can directly connect it to the suspectability of the system, which can be computed theoretically. And experimentally, we can event by event measure those so-called conserved charge distributions for different collation energies. Then we can, from those distributions, we can measure those high order cumulants. So the first measurement we have done in around 2010 that we reported the net proton fluctuation for several energies, and then later we reported the result from the RHIC-STAR scan. We have measured the net proton, net charge, and net kaon fluctuations, and the net proton is a proxy for this net baryon fluctuation, and net kaon is a proxy for net strangeless fluctuations because we cannot measure some neutral particles at mid rapidities. From the theoretical side, that actually, what's the signature of the QCD query point for this high order fluctuations? And actually, there's many model calculations. I give you an example here that which is from the sigma field model calculations. It describes that if the chemical phase line passing through the critical regions, the fourth order fluctuation will receive negative contribution and also the positive contribution here. Then the fourth order fluctuation will show this non-monotonic oscillation behavior first. Then you can see the red curve corresponding to this high energy negative contribution region. And when we go down to this low energy, which is corresponding to high mu B, then it will receive positive contribution from the critical fluctuation. Then it will show this large signals. So this is actually a characteristic signature of the QCD query point. If our collation systems, the chemical phase line has entered into the critical regions. So this is a pattern that we trying to search in the experimentally. So in the following, I will show you some details of this measurement of this high order cumulants of the fluctuations. So for net proton measurement, we have to identify the proton and antiproton. Then the proton number minus antiproton number, then we can obtain the so-called the net proton number event by evently. So to identify proton and antiproton we have actually used different, we have used both time per ejection chamber and also the time of flight. And the low PT, we identify proton and antiproton with TPC, time per ejection chamber only. And also at high PT, we need to identify proton and antiproton with both TPC and TOF. This gave us a purity of the proton and antiproton larger than 97%. This shows you this event by event net proton distribution for the in go-go clations, which is 35% to most central collation. And for different collation energies, you can see from high energies to low energies, how the net proton evolves. Basically, you can see their mean value increase as when you decrease when we decrease this collation energy. This is mainly because there's at low energy we have larger baryon stopping, and that means we have larger baryon density. That's why the proton is larger than antiproton numbers. Then its mean value is larger. So to obtain this actually distribution is efficiency uncorrected. To obtain the efficiency corrected, we have to do the efficiency correction and also some techniques to suppress the initial volume fluctuations. And so a careful centrality determination are needed. So, and this figure just shows you the distribution of net charge, net kaon, and the net protons. Here I show you the energy dependence of net proton. Energy dependence of net proton cumulant C1 to C4 as a function of the collation energy for two different centralities. The red one is 35%, and this empty marker is 70 to 80. And from the high energy to low energy, you can see this increased trend of this mean value. That means the baryon stopping. And also this high order fluctuation C2, C3, and C4. So this result of efficiency and centrality beamwidth correction has been applied. This result has been submitted into a short version paper, and a longer version paper is also prepared. And under review, we will provide more information, including, for example, correlation function, and also proton and antiproton individual cumulants. So here I show you this cumulant ratio, which is left one is skewness times sigma equal to C3 over C2, and the right one shows you the kurtosis times variance is C4 over C2, which is for net proton fluctuations. And you can see that C3 over C2 show you a monotonic increase when we decreasing the collation energies. This basically is due to this baryon asymmetries. At low energy, we have more baryons compared to proton compared to antiprotons. But high energy is mostly baryon. It's pair production dominant. So the right-hand side just shows this so-called fourth order fluctuation of this net proton number. And as I said, as I discussed with you, you can see that we see in central go-go collations, we see a clearly trend of this first decrease, and at below 20 GeV, we see a increased trend, although the error bar are still large. So, so whether we will, this is at 2.4 GeV, there's a point which is Hadis result from Hadis collaboration. And you can see that one important thing is that whether we can find a peak structure below 20 GeV. So it's very crucial we perform the very precise measurement below 20 GeV. So in second phase of the beamless scan, that we will reduce the error bar to the green band. You can see, which is between 7.7 to 20 GeV. our result will statistically will shrink to this green band. And also STAR has the fixed target mode running that we will collect the data down to 3 GeV. We will also be able to measure the result between 3 to 7.7 GeV. So we have compared our experimental result to different model calculations. The first one that, of course, is we use the URQMD transport model to compare with our data. You can see, you can see a monotonic decrease trend when we decreasing the energy. And we also use a hadron resonance gas model with both ground canonical ensemble and also the canonic ensemble. And the ground canonic ensemble, actually the baryon number is conserved on average, not event by event. So you can see this, the black dashed curve, that for kurtosis transformance, the ground canonic ensemble result will give you this flat unity result. But if we consider the baryon number conservation, which is corresponding to this HRG canonical ensemble result, you can see at low energy to show suppression trend, which is also consistent with this URQMD calculation. And also for the blue curve that we actually use this HRG with some excluded volume of this hadron resonance gas, that actually assume that these particles in the system have finite volume, that actually you cannot infinite close to each other. So actually it is equivalent to some, you add some repulsive interaction. This will also suppress your fluctuation. You see this blue curve. And so we have done actually a statistical test to describe whether our data can be described by those models. We have tested those and with chi-square test and obtained the p-value below 27 GeV. We found that actually the trend of the data cannot described by those models. You can see the p-value; they're all it's very small.
Excuse me, Professor Luo, but your time is over. So please go to conclusions. Then we can come back to other slides during the discussions. Okay.
Okay. Sorry. I will
go to conclusions.
Okay, I will discuss. Sorry, I will discuss my summary and outlook. And so we found that the yield ratio of light nuclei and the fourth order net proton fluctuations in central collisions show this non-monotonic energy dependence, which could serve an important experimental basis for the critical point search. And we need a large statistic to measure those higher order fluctuations. And also, and in future, we will study this high baryon density region with high precision with those, for example, the future facilities. Okay, that's all. Thank you.
Thank you very much for your very impressive talk on both theoretical, experimental side. Unfortunately, we do not have time for even short questions. Therefore, I ask everyone, please reserve the questions for the discussion, which will be later. Okay, now please stop sharing your screen and I call, thank you.